Okay, so today we're going to cover a lot of a survey of different topics, okay? And given the fact that we're short on time, we're not going to do any of the questions. Yes?
Is the concepts covered today going to be on the exam?
Probably not. But pay attention. Okay, so with that introduction, what the concepts today are just good for you. Okay. All right. So what we're going to talk about is sort of more advanced MR, things that you'll probably see if you get into MR more, or things that you're going to see in the future. So the first thing we want to talk about is what happens when spins move. Okay. And so the idea is MR is actually sensitive to flow, and a lot of MR is imaging of flow. And that's really important because in biological tissues, if things don't move in a biological tissue, then that's generally a sign of something's going wrong. So today we're going to spend the first half of the lecture talking about how do we measure things that move and then get some more insight into the biological tissue. So let's say we have two spins A and B, okay? And at time equals 0, they start off at some location x, all right? And we have this gradient here, the g sub x gradient, that is a negative gradient. So it's decreasing in the x direction. At some later time, we assume A is stationary and B has moved. So this is A and this is B. And B has moved out into a stronger part of the gradient field. Okay? So we look at the relative phase difference. A has sort of lagged behind by 90 degrees, and then B has gone counterclockwise by 135 degrees. So there's actually a phase difference depending on where they've moved, because B has gone into a stronger part of the field. So B's experienced this part of the field, where A is still experiencing that part of the gradient field. All right. Now, so this is some time, let's say we said some from 0 to t. Then we wait some time. We look at the things at twice that time. And what happens is, and during that time, we apply gradient in the opposite direction. Okay. So now spin A, which experienced a negative gradient for half its time, now experience a positive gradient of exactly equal and opposite for the next half. And so those two effects cancel out. All right. So this has a phase of 0. Okay, so any static spin in the presence of what's called a bipolar gradient is going to have a spin of 0. And then this guy moves out into even a farther part of the field. And so it went minus 135 with the first gradient, but since it keeps moving out, during the positive gradient, it overcompensates and over-rotates. And so now it's at 45 degrees. So it's got a net phase of 45 degrees. And that phase depends on its velocity. So this is how we're going to measure velocity with MRI. Right? So the way to do it is the phase of any spin is given by its delta omega integrated over time. We know delta omega is just gamma times delta B. And then here's the part that we looked at before. So we had this gamma g times r before, g dot r. Okay? And previously, these x, y, and z we assumed didn't depend on time. All right? So remember you had things like gx, x, plus gy, y. Okay? But now we're going to assume that they have some time dependence. Okay? So time. And so we just want to model that time dependence very simply. So we're going to consider the very simplest motion where we've got some initial location, some velocity, and some acceleration. Okay. And then it's just very simple calculus. We replace x with that expression. It's all integrated over time, and so we just have to integrate the tau or the tau squared. And so what you end up with is sort of these, you have the integral of the gradient. That gives us the first order moment. You have the integral of the gradient times time. That's the 0th order moment, the 1st order moment, and then here you have the 2nd order moment. All right. So basically, we're just looking at the moments of the gradient, and so that's just repeated here. So the 0th order moment is just the integral of the gradient. Okay. So if I have a bipolar gradient which is equal and opposite positive for some time and negative for some time, what's the 0th order moment of that gradient? 0. Okay. So where am I in k-space at the end of that gradient? Center of k-space. Okay. So this is bipolar gradient like this. M naught is equal to 0. Okay. So what we're really going to focus on is the 1st order gradient. And so in the case of a bipolar gradient like that, it turns out the expression, so the 1st order moment, the 0th order moment is 0. And the 1st order moment, just with simple calculus, is just g naught times t squared. Okay? So where t is the width, and in this case we assume we apply them right after each other. So that means that if I come and apply a set of gradients like this, I can get the phi is equal to gamma times the velocity times g naught t squared. Okay. And typically in MR, and this is what we use to create what's called phase contrast angiography. So typically in MR, we'll acquire another set of gradients, phi over 2, to get this phi 2, and that's going to be minus gamma vx g naught t squared, because this minus comes because now we flip the sign of the gradients, so the 1st order moment has changed. Okay? And then if we take the difference of those two, we get something that's proportional to velocity. So we can just measure this change in phase, and then since we know g naught, we know t squared, those are things we program, we can estimate what the velocity is. All right? So, yes, question?
How do those not equal to 0, like the 0? Just look at the diagram, shouldn't I cancel out?
You mean the top and the bottom gradients? Yeah. Okay. So this is going to have, so if you think about 0th order moment, 1st order moment, the way to think about 1st order moment is imagine these as weights. And if you imagine a weight like this and imagine a weight like that, if you think about pulling those two things, the 1st order moment is whether that's going to rotate or not. Okay, so it's like this, right? So that has a 1st order moment. And then this has equal and opposite 1st order moment because it's going to rotate the other way.
So it's not, so that's all happening at once, it's not with respect to time.
Well, this is a function of time. Yeah. It's just a useful, I mean, if you look at the expression, it's just you're taking the gradient and multiplying by time at every point in time and then integrating that thing. Okay. So I'm taking that waveform and I'm multiplying it by t, right? And then that's the integral. Okay. So here's an example of phase contrast angiography. So we're looking at vessels coming off the circle of Willis in your brain. And so here, the gradient has been applied in the what's called the AP direction, so anterior to posterior. And what you're seeing here is these white things are showing the flow of the blood going towards the back of your brain. Okay. Here the gradient's been applied this way in the right-left direction. And so you would expect, as you expect, the blood on this side flows this way, and the blood on this side has a negative sign and flows the other way. All right, so the phase contrast angiography tells you which way the blood is flowing and also how fast it's flowing. All right. You can also, a really cool application of this is something called 4D flow, which is done in the heart, where you actually measure the velocity at every heartbeat in different directions. And you can see different parts of the heartbeat. You measure at different parts of the heartbeat, and you can sort of see what the blood flow looks like. So if you look at this movie here, this is going to show you velocity fields going through the blood. Okay. So that's pretty cool, right? And a fun fact is someone who took this course back in 2004 or 5, who's now a faculty member here, actually did a startup company, Arteris, that actually commercializes all this stuff. So if you ever have a heart problem and they use that software, then that's basically the method they're using. Okay. Okay, so we're going to talk about one thing that can go wrong is that if we're talking about phase, we've already seen this a little bit in MR, which is, there's ambiguity. If I go this way versus this way, I don't know which way the blood went. I don't know if it went left, got me that phase, or went right and got me that phase. Okay, so there's an ambiguity because we're using phase. So the vanc is defined as the velocity at which the phase is 180 degrees. Once we go beyond 180 degrees and we're not really sure where the blood came from. So for example, if I'm at a point here, I don't know if I went this way or I went all the way around. Okay? So that's a form of aliasing. And so this is an example of aliasing in the pulmonary artery where the vanc was set too low. They set it at 15 centimeters per second. Okay? So what happened was that looks like blood is going in two directions. There's the white part and there's the black part. Okay? And so if you didn't know that, you would think that maybe there's some weird turbulence in this vessel. Maybe we need to do surgery on this guy. He's about to die. Okay? But it turns out that it's actually the vanc was set too low. So once you set it to 30 centimeters per second, then all the blood is going in the right direction. So there's no appearance of aliasing of blood coming in the other direction. Okay. Another example where that can occur is in any large vessels, you can have laminar flow. And so typically the flow is strongest in the middle and then weakest near the vessel walls, and so you can have velocity aliased in the middle of the vessel. So you can appear as if blood's going one way here and the other way somewhere else in the vessel. Okay? Yeah.
So how would you set a, I guess, bank that prevents that? Because if you, in the previous example, you said to 15,
Yeah.
then it was too low, but then, like, if you have that gradient, so how do you just set it to the maximum?
Typically in clinical practice, yeah, people sort of know what the vancs should be. But what it could be is there's two approaches. One is you can, let's say you get something that doesn't look reasonable, then the technician, if they're savvy, will maybe just acquire another scan with a higher vanc. The other thing you could do is you could acquire at different vancs, and then if you take the difference, you can also sort of solve for what it should be. But the bottom line is you have to acquire more data. Okay? Yeah, it's a question.
If you're looking at like a particular blood vessel, can you say that you know which way the blood is flowing and then interpret up to 2 pi instead? That it is going right.
Yeah, but you would want to. Right. I mean, the phase contrast tells you which direction the blood is flowing, right? It gives you its estimate of that. But you would still want to know if you had flow going two ways, and that occurs in places like the heart, right, where sometimes you have regurgitation, you have flow, back flow of blood, which is not good, which means you need a new valve. You would want to know if that's due to the MR acquisition or due to physiology. You can't just make the assumption. Okay. Any other questions? Okay. So we're not going to do these questions, so we're just going to skip over them. Okay. Just because of the time issue. So the other way we can do angiography in MR is, it's very simple. It's called the inflow effect. And the idea here is, if I have a region, it's very similar to sort of the background suppression we did last time, where if I have a region of tissue, okay, and I keep applying RF pulses to it, then the magnetization in that tissue never gets to recover. There's no T1 recovery, right? I just keep hammering the tissue. But the inflowing blood doesn't experience all those RF pulses, so it has relatively higher magnitude than the static tissue. So we create a contrast between things that are moving and things that aren't moving. Okay? That's what's known as the inflow effect, and this is shown here where basically all the new blood coming in is not as saturated as this black stuff here in the middle, which never has a T1 recovery occurring to it. Okay? So the inflow effect actually was sort of first considered as an artifact, like, oh, all of a sudden these things appeared bright in the image. And even in some images, it's still now, if someone says, oh, there's an inflow effect, it's referred to as an artifact. But it turns out that it's actually also a really useful imaging thing. So these are time-of-flight angiography, so no contrast. We're just looking at the difference in the magnetization between the flowing blood and the static tissue. You can have these really nice images of the vasculature. Okay? And this is a really common theme in MR and probably all of medical imaging, where oftentimes something will appear as an artifact and people try to get rid of it. And then later on, maybe it may take 10 years, someone realizes, oh, this is really useful information, and it becomes a new technique. Okay? So oftentimes the gold is in the garbage. Okay? And so as you're doing your research, oftentimes the things that don't make sense are where you're going to find your next discovery. Right? So don't be too quick to dismiss things that aren't right, okay? Because sometimes they could be really useful. Okay, any questions before we move on? Okay. So the next thing we're going to talk about is diffusion, and we're just obviously, once again, just give a very high-level view of diffusion. So diffusion, as you all know, is the random motion of particles. And for most of what we'll talk about, we're really concerned about the random motion of water, okay, which is constantly diffusing in your body right now. If it wasn't diffusing, you would all die. We would all die, right? I mean, it's setting up gradients and all sorts of wonderful things right now, okay? So the main thing with diffusion is the longer we wait, so this is time, the more things get spread out, okay? And sort of a measure of that is sort of the standard deviation of their position, which is the square root of 2 times the diffusion. So diffusivity, D, tells you how easily things can diffuse, and then time is just how long we waited, right? So this is showing the distribution of particles at 1, 2, and 5, and 10 milliseconds. And basically the idea is the longer you wait, the more things just spread out, which we all sort of know intuitively. If you had perfume in here, it would just sort of expand out. Okay. And so that's in 1D or 2D or 3D. The only thing that changes is whether this is a 2, a 4, or a 6. But there's always going to be that square root of dt. Okay. So how do we measure diffusion in MRI? Well, it turns out it's very similar to how we measure velocity. It's just the way we interpret it is differently. Okay. So once again, we're starting off with 2 spins, A and B, but now we're going to assume that they're both moving. Okay. So they both accumulate net phase. Okay. And then so from time 0 to t, we have a negative gradient, and then from t to 2t, we refocus the gradient. But since these guys are moving around, they're not going to be refocused perfectly, so they're all going to acquire net phase. Right? And the idea is, if we think about a lot of these spins, the more they move around, the more they're going to be dephased. And so we think about the sum of the spins, it's going to go down. Okay? So if diffusivity goes up, more diffusion is going to be more dephasing. So dephasing is going to go up, and so the magnetization that we get is going to go down. All right, so that's the basic idea behind diffusion. So that's shown here, where the spins are without diffusion. If we apply a gradient, a plus gradient here and a minus gradient here, then at the end of the day, we're completely rephased. Okay, and that's just what we've seen in imaging. So that's the center K space. Right? With diffusion, you notice this spin here moves, so it doesn't get the rephasing, okay? And so the overall vector sum is going to be less. And that's shown here, where, and then we can sort of sensitize the MRI experiment to diffusivity. So this gradient value, I can have a small gradient, let's say G1, or I can have a big gradient, okay? The bigger I make the gradient, the more the spins as they move are going to experience different magnetic fields, so there's going to be much more dephasing. All right. And so what that leads to is the signal we measure in diffusion is exp minus b times d, where this b is called the B factor. Okay. And one of the things that makes the B factor bigger is the gradient amplitude. Okay. The other things are these timing intervals. Okay. So for example, the bigger I make the gradient, the more things are going to decay with some diffusion. And also the longer I wait, the more things are going to decay because they're going to diffuse more distance. Right? So this is an example of, and this is why diffusion is so important and is still used clinically quite a lot, is this is a T2 weighted image of someone who has a problem. Okay? And if you look at that image, it doesn't really, nothing really shows up that clearly. It's not like it sort of yells out at you. But if you do a diffusion weighted image, clearly this person has something going on. Okay, and what the experiment, the observation in the early 90s was that after a stroke, the diffusivity goes down. Okay, so in this case, diffusivity goes down, so e to the minus bd is going to go up. All right, so in those areas of the brain that are, sort of have been damaged by stroke, it appears that diffusion goes down, and therefore the MR signal goes up. And that's been one of the really main applications. So anyone with a stroke will typically get a diffusion-weighted image as standard protocol. Yes?
If you come into the hospital, like, when you get a single MRI, do you have to retake scans every time you want to see different weightings, or do you just recalculate a single scan?
That's a good question. We're going to revisit that. Right now, the way it's currently done is different scans.
So then when you do go in, do they do like a T1, a T2, a density, and then a diffusion weighted in addition to like an angiography and like all that in one? Like, do they just put you in and run every single test?
Depends on how sick you are.
Okay.
Yeah. I mean, if you're really, like if you've just been hit by a car and you're hemorrhaging, they won't even do an MR in general. They'll just get you to a CT. So if you're very close to death, they'll put you in a CT and get the scan within just look for major damage. Because if you're really that damaged, they're just going to get into surgery as soon as possible. So they just want, a 5-minute scan, you're in and out. Now, if you're sort of still okay, then they might have time for a longer scan. And because then the clinical decision making becomes much more complex. Because if they're not going to do surgery, then the question is, do they give you like a clot busting drug? But then the question is, sometimes that can exacerbate the stroke, because then you open up something and then it puts too much flow in. And so that's still research, actually. It's still not known what the best thing to do is for stroke.
How long would it take to do all of these tests?
It depends on the resolution. So if you might want to do a 30-minute exam. But if the person was sort of okay and you were doing more research, you might make it an hour long. But typically, I think people would like to get it with less than 30 minutes. And I know that in our department, I think the goal is to try to get it down to 10 minutes. But there's always going to be a trade-off. Okay? And we'll talk about some ways of reducing that trade-off in the last half. This is another example where, once again, on T2, you sort of see something going on there, but it's not super obvious. It's clearly very obvious on the diffusion-weighted image. And then if you look at the angio, then clearly this person, where there should have been blood flow, it's been cut off. Okay. So we'll skip those questions. The other sort of main application of diffusion is comparing whether diffusion is isotropic or anisotropic. So the idea is, if I have a tube, right, it's much more easy for the water to flow along the direction of the tube to diffuse that way than it is to diffuse here, okay? Because it's going to hit the boundaries, and so it can't really go beyond the boundaries. So we have a lot of sort of tube-like structures in the body, and one of the main ones is all the white matter fibers in your brain, which are sort of like these fibers that go quite long distances sometimes. So we want to be able to measure that, and then the way we measure that is we basically measure diffusion in different directions. So for example, here, if we do a horizontal gradient, it's sensitive to horizontal motion, so there's signal loss there, but it's not sensitive to vertical motion, so there's no signal loss in that direction. Okay? So you sensitize yourself to diffusion in this direction, and then here, with a vertical gradient, we sensitize ourselves to diffusion in this direction. Okay? And so you can just keep doing this over and over in different directions. And so typically that's what's done. And then when you do that, if you acquire enough directions, you can sort of start characterizing the shape of diffusion. And typically what's done is, the minimum we really need is to define an ellipsoid. Okay? So that requires at least 6 parameters. So with diffusion tensor imaging, there's at least 6 diffusion directions plus one without diffusion weighting sort of as a baseline. So it's typically 7 directions. Okay? And what that's used to do is to define what's called the diffusion tensor. So that's the diffusion tensor. And then the imaging is called diffusion tensor imaging, or DTI. So if you hear the term DTI, or you have, say, you go in for a scan and someone says it's a DTI scan, then this is what they're doing. They're doing lots of different directions on you. Okay. And then it turns out from that they can figure out not only the shape of that ellipsoid, but also which way it's pointing. Okay. So the shape is useful because it tells you how anisotropic the diffusion is. So for example, and then the direction is useful because it'll tell you which way the water is going or which way the fibers are going. So these are three ellipses. They have the same anisotropy, right? They're the same shape, but they just have different directions. Okay. So the two thing is we want to measure the shape. We also want to measure the directions. And so then what we get at the end of the day is we can have this is sort of the overall mean diffusivity, or MD. Okay. That's sort of how diffuse things are. And you can sort of see that the lowest diffusion is here in the white matter. Okay. Things don't diffuse very well in white matter, as opposed to the CSF. There's lots of diffusion because it's free water. And then in the gray matter over here, there's relatively more diffusion. But what's different about the white matter is it's very anisotropic. Okay? So these are different measures of anisotropy, and you can sort of see those are highest in the white matter, which is basically where the diffusion has a directionality to it. And then you can do nice color coding where you can sort of, these colors show red, blue, and green show which direction the fibers are going. So that's one level you can go. But you can take it to the next step. You have all these little ellipsoids with directions, right? So you can just sort of try to do some ray tracing and try to figure out where the fibers are going. And if you do that, you can start making really nice sort of what are called fiber tracks. All right? And so this was an image I think I showed in an earlier lecture. So this is the fiber track you would get with diffusion tensor imaging using not just 7 directions, but many, many directions over 8 minutes. Okay. And so this is rather remarkable. Basically, this is just taken from a normal human being lying in the scanner and measuring diffusion in different directions, and then sort of following the direction of the fibers. And so you basically, at the end of that 8.5 minutes and some more processing time, you actually have a really nice wiring diagram of your brain. All right? So this is really useful because basically, and if you're waiting to wait longer, then you get much more detail. But I think this is relatively remarkable in the sense that there's really, before DTI came along, there was really no good way to do this, even in cadavers, right? Because even in cadaver, I mean, all you could do is put some agent and follow it, maybe one fiber, but then you'd have to do it over and over again for every little fiber. So even if you could sort of take someone's brain out and freeze it, it'd still be really difficult to do this. Okay. And so one interesting application, for example, is they're now scanning babies and looking at how babies' brains develop and how long it takes to develop the pathways. Okay? And certainly what brain imaging has shown is that your brain is really still maturing up to about the age of 25. Okay? We can still, with MRI, see major changes in connectivity and gray and white matter densities until about 25. Okay? And I think the joke is that the insurance companies figured this out many, many years ago because the insurance rates sort of plateau they're really high for young males, right, who like to drive their cars really fast, until about 25, and they sort of normalize, okay? And that's when your prefrontal cortex decision-making is fully hooked up and hopefully online. All right. Okay, so that's sort of a very quick overview of diffusion tensor imaging. So any questions? So those are 2 main ways that we use MRI to look at motion. What we're going to do now is switch gears and talk about sort of the latest advances in MRI and where MRI might be going. So one issue with MRI is right now it's a fairly costly technology. So a standard sort of fully decked out scanner is about $1 million per Tesla. Okay. Roughly $1 million. You can usually bargain it down to a little less, but it's still very expensive. Okay. So one of the ideas is, how do we make it more inexpensive so it's more accessible to a wider range of people? So this is showing most of the cost is in the magnet, and then the next is the gradient coils and the gradient amp. So those tend to be the very high power, lots of infrastructure things. And then everything else is sort of fairly small in cost. So a lot of the work has gone to, what can we do with the magnet? What can we do with the gradient amp and coils? All right. So does anyone here know who Michael Crichton is? Yes. Who is he? He wrote Jurassic Park, right? And a bunch of other stuff, right? So he wrote this thing, which I have not read, called Timeline, but it is, and he was a medical doctor before he became a writer, so he researches his books very well. And this is actually pretty good. So the ordinary MRI does this with a very powerful magnet, say 1.5 Tesla, okay, which is about 25,000 times as strong as the Earth's magnetic field, which is pretty close, right? I mean, he's actually done his research here. But he's saying in the future, we don't need that. We use squids, which are superconducting quantum interference devices that are so sensitive they can measure resonance just from the Earth's magnetic field. We don't have any magnets in there. So he's saying in the future, you'll just have these squid detectors and you just walk in and there's no magnet and it'll do MRI on you. And the idea is, the reason for the big magnet was to get that net magnetization. And the bigger the magnet, the bigger that magnetization was. And so that we have a bigger signal to detect. The idea is with a very low field magnet, you still have a magnetization, but it's very small, so your signal level is very small. But if you have a very sensitive detector, then maybe you can measure something that's useful. So that's the idea behind using squids. So this is some work done up at Berkeley, where basically they have a very small permanent magnet there. Okay, so just a little magnet there, which is creating some field, a little higher, probably about 20 times the Earth's magnetic field, so like 60 microtesla or something like that, or maybe 300 microtesla, I think, is what it was. And then these other coils here that you see are the gradient coils, typically. And then here's where the squid is, here, okay? And that's what's doing the measurement. And so amazingly, it's at 132 microtesla. So it's basically about 2 times the Earth's magnetic field. Okay, so not much stronger. And amazingly, so this was the pepper, and this is one of their first MR images of the pepper. Doing with 48 projections and 1.5 minute acquisition. And later on, at the same field, this is the person in the magnet, and this is a picture of their brain. Okay, so not great, not good enough for clinical work, but sort of a proof of concept that maybe this is something that could be used in the future. Okay, yes.
So do you know how this will actually go anywhere? Because you said that 20 years ago, 20 years onward, instead of going to like 132 microteslas, trying to go to 7.
I think there's going to be there's 2 main things. One is that people who are doing research and just need all the signal they can get, they'll still keep pushing higher magnetic fields, right? But in terms of getting more broad, application of MR to places that may not have the infrastructure, that's going to push the low cost. Even things like the military wants battlefield MRI, right? So they're also putting a lot of money into it. Okay. So this is one of those efforts that was I think a PhD thesis out of MIT, where here the idea is this is now the permanent magnet. This is what's creating the B0 field. Okay, so it's creating some B0 field, I think probably in this direction. Okay, and then so you have a the magnets are just permanent magnets, and then what happens is instead of the gradient coil, okay, the magnet's in homogeneous field, so you just rotate this magnet around, sort of like CT, okay, and that's the gradients, okay. So the GX and GY gradients are just taking this inhomogeneous field, which has a component that's homogeneous, but then you also have these components that are inhomogeneous, and so this is showing this here, where you can sort of see this is on rollers here, and they just sort of roll it and put the sample inside, okay. And from that, I mean, here's some early images that they could get. Showing that it's actually at least doable. The concept at least makes some sense. So this would be a great application because, for example, you could literally think of just someone, riding a bike, and turning this gradient or hand cranking this gradient. Okay, you wouldn't need any power, hardly at all, except for the RF electronics. Okay. Here's another one out of the same group where they basically designed this cap that you could move around the person like this. And so this is an example of what that cap looks like here. Okay, and it's just a bunch of these little magnetic blocks that they've designed to set up a B field in some direction. Then they put some wires to make the gradient fields like that. So that's the gradient field. And then they have some more wires for the RF transmit. So if you look at here, this here is the RF. Okay, here's the B0, and here's the GX and GY. Okay, or I think they did GZ and GY there. Okay, and so with all that together, they imaged this phantom here, and these are the images they get. Okay, which are not that great, but it's a proof of concept. And this was just published this year in 2019, so this is still state of the art. So it's just showing that there are people trying new ideas in MR and seeing if there are ways. And so in this case, I think that they said that this magnet, yeah, you can make this magnet for less than $500. Okay, and probably the other parts, you could probably get this down to $1,000 if you really tried. So this is a total paradigm shift. Whereas 1 hour of scan time in a hospital is like several $1,000s. Okay, so so how far this will go, I'm not really sure, but this is what people are working on for portable MRI. The other thing that's actually already used clinically, and what we're going to do is sort of the last part of this talk is going to be telling you all the ways that people are trying to go beyond the concepts we talked about in this course. So in this course, we talked about sampling. We said you had to satisfy these different criteria. You had to sample K-space. If you had an FOV, delta K was this. If you had a certain resolution, you had to cover this much K-space. Now I'm going to tell you all the ways people have tried to break those rules. Okay, so basically going beyond the speed limit. Okay. So the first thing that happened in the late 90s or early 2000s was people realized that what happens if instead of having just one coil receiving the magnetization, you had lots of little coils? Okay, and this led to something called parallel imaging. And so you can sort of see here, there's different coils here, okay, and here lots of different coils, okay. And so each coil is going to see a certain part of the image of the body. And so that in and of itself is giving you information about the object, right? It's getting spatial information. So you would think you don't need the gradients to do all the work. So the idea is you're going to split the work between the gradients, which is all we've talked about so far, and these coils, which can get information about where things are. Okay? And I think there's going to be one of the groups is going to talk a little bit about parallel imaging. So here's the basic idea. Up to now, we've just imagined that there's just one coil, right? And this is like the K-space, so we measure K-space. And this is the magnetization that we actually care about. So this is like the M, okay? So that's the object we care about. And it turns out that these components here in the matrix were basically Fourier components. So traditional MRI assumes that that matrix is the Fourier components, such that what we measure, the K-space, is just a Fourier transform of my object. So then if I want my object, I just say F equals F inverse, let's call this S. Okay, so that's traditional imaging. Okay, but what that means is we have to make that F very special. It has to be full rank, it has to be orthogonal, it has to have all these nice properties. So that's what we've talked about so far. Okay, it turns out that we sort of had to lie to you, right? Because the F is not really ever perfect, because the coil always has some sensitivity that's not uniform. Okay, so what we actually measured is S, instead of what we've told you is this: the signal is equal to the Fourier transform of the object. Actually, what it's equal to is the Fourier transform of, let's say, some coil sensitivity. Okay, so what you actually measure what you actually get from, so what we get then is Cm equals F inverse S is basically some measure of my object multiplied by the coil sensitivity. Okay, So what parallel imaging does is say, okay, well, let's just model that explicitly. And we have different coils here. And so each one of these is going to have an F. Its E matrix we can consider being F times the coil sensitivity of the first coil, F times the coil sensitivity of the second coil, F times the coil sensitivity of the third coil. Okay. And so now we've got this long skinny matrix, right? And so for those of you who've had some linear algebra, you know that this is an overdetermined problem, right? And then what we can do is, if we know E, we can say that our estimate of M is just going to be E transpose E inverse E transpose S. Okay, so that's what's called generalized imaging. Okay, so the idea is, instead of all this Fourier stuff, we can now just think about things in sort of more linear algebraic terms, where we basically have some data we've measured, S, and we're trying to get back to come up with our best estimate of what object could have created that. Okay, so that really sort of is a paradigm shift. And so the other thing, if you look at this, you can say, well, I don't really need my matrix to be that long and skinny, right? I should be able to skip some lines in k-space and still have a matrix that's invertible. And that's the idea behind parallel imaging. So this actually came out, so there's two main approaches to that. So the basic idea is, what we've told you so far is, if you skip lines in k-space, you're going to get aliasing. Okay, and that's still the case. So if every coil, if I skip lines in k-space, every coil is going to have an aliased image. Okay, so that's shown here. I have 4 coils looking at my object, and each of them has some aliasing in it. Okay, but they all have a different view of my object, so it turns out I can put those into a linear equation and solve and get my object that I care about at the end. Okay. So that's one way of looking at it, that basically we've lost information in k-space, but we've regained it because we have that spatial diversity, because those coil sensitivities are different. So parallel imaging is now standard. Okay, I mean, within 15 years, it is now, any scanner you go onto will have parallel imaging, because it allows you to go faster, because you don't have to acquire so many k-space samples. Okay. The other way you can look at things is, you can have my object is here, and I multiply it by some coil sensitivity pattern. So what the coil really is picking up is something like that, right? It's my object times the coil sensitivity, which only sees part of my object. What that means in the Fourier domain, this is the Fourier domain of my whole object. I multiplied here, so I must convolve with the Fourier transform of this guy, and that's going to blur out the information, right? So that means that if I have neighboring information in k-space, now it's all somewhat related. Different neighboring points are related to each other because I blurred it all, okay, with this convolution. And so what that means is that, let's see, what's the example? If I skip lines in k-space now, I can estimate what the missing line should have been, as long as I know what that blurring function was. And so this is another way of going about it. And so that's the other way of doing parallel imaging. Okay. So both these are used in practice. They're both available on different vendors. And this is just showing an example of, here I've skipped, R equals 2 means I've skipped every other line in k-space. Okay. This means I've only kept every third line in k-space. I've gone 3 times as fast. So both of these are examples of showing that you can go beyond what we've talked about in this course. So this is twice as fast here and 3 times as fast here. Now in this case, once they started going 4 times as fast, they started ending up with problems. Okay, but a lot of that's just if they used a different coil or did something differently. Routinely now, people accelerate at least 4 times as fast, and going up to 8 times as fast or more is actually sort of the state of the art now. Okay, so there has been this really dramatic decrease in speed, or decrease in time and increase in speed over the last decade or so. So that's just summarizing that. The next sort of major breakthrough was something called compressed sensing. Okay. And here the idea is, here's my object, here's its Fourier transform, and now I'm just going to randomly throw out like half the data, or 80% of the data. Okay, but the key is I have to do it in a random fashion. Okay. And so if I just took this data and did sort of a normal reconstruction, I get something that looks really bad. Okay, it's not going to be a very good image. But if I tell my algorithm that, hey, you know, this is an object that has some smoothness or some other properties, or it has some properties of an image, then it can actually do a very good job of reconstructing my image. Okay? And so this is another thing that now all the vendors are offering to go faster. Basically, throw away data, but because we're not imaging anything, we're imaging objects, and objects have certain properties, you can make use of that prior information to constrain your reconstruction. Yes?
Did you miss something with that? Especially if you're looking for like something really small in the brain.
Yeah, so that's the question is, are you missing something? And so there's been a lot of debate in the field about, you know, can this be used clinically? And I think the consensus is now that you can use it clinically. I mean, it is sort of FDA approved now, but there was a lot of research that went into sort of showing that you could do that. Okay. Yeah.
I just don't like it.
Yeah, well, some people don't like it.
Because
Yeah.
if you have something like a really, like an aneurysm, and you're missing that data point, and then it recreates it to like miss that aneurysm.
Yeah. Well, if you don't like this, you won't like the stuff that comes later. Okay, which it gets even more interesting. Okay, question.
Why would you want to do this? What is the advantage of
Speed. It's all about speed. It's basically getting the subject in and out as quickly as possible. So, for example, one of the first groups to really push this was a group that did pediatric imaging up at Stanford, and there the idea is, you know, if you have a kid, you know they can't stay still, right? And you don't want to sedate a kid, right? For standard imaging. And so basically, the faster you can go, there's a trade-off, right? I mean, you're collecting less data, so your signal-noise ratio will go down. But it's much better to acquire it quickly and have an image that doesn't have the kid moving around versus if you acquire longer data but they're moving around, then your data quality is also going to be bad. So that's the idea, that speed. So this is actually, here there was a 10-fold undersampling of the data. Okay. So basically here is if you use all the data that we've talked about, that's Nyquist sampling. So you get a really nice picture of the vasculature in this person's leg. If you throw out a lot of the data, then you can have either a low resolution or sort of a linearly interpolated version of the data. But they're both much worse than Nyquist sampling, which is what we've talked about in this course. If you use compressed sensing, then it does a remarkable job of recreating what the image should be. I mean, so much so that you think it must be cheating, but it's not. I mean, this has been verified many, many times. Okay. Here, once again, we have, these are angios on the bottom. Okay, so full sampling of the data. These are full sampling. Okay, so that's what the image should look like. Here's when in this row, we've gone by a factor of 3.4. Here we've gone by a factor of 6.4. So we've gone 6 times as fast in that last column, but arguably most of the information that you care about is still there. So that's a huge gain, right? You can go from a 10-minute scan to a 1.5-minute scan. And so that's really important for some applications. Okay. The other main thing is just forget about MR imaging. Okay. And this is something called MR fingerprinting, which is also being offered by some of the vendors. And the basic idea is this, that remember we talked about the block equations? Those are the governing equations of MR. So basically, if you can model that equation, then you can come up with any pulse sequence you want. So this is this pulse sequence here, where they just basically threw in random flip angles, gradients, just throw everything in there and just randomly tweak things. And then you use the simulator to predict what the magnetization should look like given different parameters. So you basically create a dictionary. You say, if the world was like this, then the MR signal would look like that. If the world was like this, it'd look like that. And then then you just match what you measure to the object, and you estimate it, and you sort of come up with your best estimate of the object. And so for that case, basically, in that case, you just skip the imaging completely, and you go directly to estimating. So this is what happens if you try to estimate the image using the methods we've used in this class. These are images that you get if you use MR fingerprinting. Okay? So it totally sort of, all the concepts in this course, it just throws them out and says, if you don't need those concepts, You just model the whole thing. And that really represents sort of, the paradigm shift, because basically right now, you can do things now that you couldn't do 20 years ago because computers are so fast. You have so much memory, so much storage space, so much computing power that now all these methods that would have been silly 20 years ago make a lot of sense. Okay? And that brings us to deep learning, right? Which has only really taken off, in the last 5 to 7 years, partly because computation, you can actually do the computation now. So all the money that went into getting video games and GPUs, that's all now being used by medical imaging because it's the same calculations. Okay. So what's the idea behind deep learning? So what we've talked about in this course has been fully Cartesian MRI, which is just one kind of MRI. And for that, we've talked about the conventional reconstruction chain. We've talked about Fourier imaging and K-space and how all these things are really super important. And if you do all those things right, you can get a nice image. Okay? So the deep learning approach is saying you don't need to know anything about that. Just let the computer figure it out. Okay? And let's see what the computer can do. So here's the idea. We're going to just throw in our case. So this is still going to be our MR data, right? So we can still consider this the K-space data. But the computer knows nothing about K-space. Okay? The way they trained this doesn't even know about MR. What they did is they went to ImageNet and just downloaded lots of images. Okay? And then just trained this algorithm. And then tested it on MR images, which it had never seen before. Okay? So it wasn't even biased towards MR. And then they used this architecture where you have some fully connected layers and some convolutional layers, and then you end up with your image at the end. Okay. And remarkably, what they found was that they did really, really well. So for example, this is the reference image. So this is as if you kept all the data, and this was the actual original image. And then what they did was they imagined sampling this with different sampling. So in this case here, they undersampled it, and here they misaligned the Fourier data. So even the lines in Fourier weren't acquired correctly. So they did everything wrong, right? It's like they didn't acquire the data correctly. So if you do everything wrong, the normal algorithm will just fail. Okay, so if I give you the wrong data set and you use traditional Fourier imaging, it's going to give you the wrong answer. But if you actually train this algorithm to make the images look correct off of the internet, then it fixes that for you and creates a really nice image. Okay. And in fact, it does just as well, or maybe even better than compressed sensing. Yep. Question.
Is it able to reconstruct abnormalities?
Yeah. It is. Which is sort of amazing because in these images it's shown it's never even seen in MRI images. But the thing is that biological things just tend to have certain features. Okay, so when you have a tumor, it's generally not going to be really spiky and noisy. It's going to have certain biological features. And so the idea is that the images you see in the real world, the images, anytime you're looking at biology, you're going to have certain themes that repeat over and over again. And so it's sufficient to look at lots of natural images and learn those features that are important. The idea is if I have an n by n image, right? So that means that I have n squared possibilities, right? Well, more than n squared. So there's n squared voxels. Each one, let's say, could take on a million different values. So I have n squared times a million different possibilities of images that I could have, right? But when we look at the real world, we don't see all those possibilities. We only see a certain part of those possibilities because we're looking at objects that have evolved over time. We either see trees, or we see buildings, or we see humans or animals, and those basically span a relatively small part of that big space. And so what we've done in this course is we said, assume we know nothing about the image, then we have to design something that can handle that whole space. So whatever image you throw me, even if it's totally non-biological, I want to be able to reconstruct it. But that means I'm doing overkill, right? I'm being much more conservative than I need to, because to reconstruct something biological, if I know I'm in this space, I can make trade-offs, and that's what allows you to go faster. The deep learning networks basically come up with a probability distribution of the world and the probability distribution of what the parameters could be, and it says, well, the most, if the object is from this world, then it probably is going to satisfy these things. Now, those of you who know deep learning there's still a lot of debate about how easy it is to trick deep learning networks, whether you could come up with something that's totally bad. So the vendors have spent a lot of time validating this, and what I've heard from them is that they feel confident that I think the FDA maybe just approved their first deep learning application to MR this year or maybe early next year. All right. So it is something that is sort of, when you first, it sort of is a bit surprising, but the idea is these networks are really, really good at characterizing the probability of the world. And then they can make optimal use of that. Okay. So I'll just show you one example of it before we finish up. So here's an example where they had high resolution images of, I guess, someone's knee, okay? And then what they did was they threw out, they kept only every, maybe 10th row, okay? So then they end up with these low resolution slices. And the idea is, if I only have the image here and here, can I figure out what's in the slices in between? Okay. So the typical approach is to interpolate it, sort of average and figure out what might have been in those slices. So their question was, can we use a deep learning network to get to super resolution and figure out what might have been there? And the idea is, what's between these, because of how images are and how biology works, this has a lot of information about what could happen in here. It's not like anything can happen between these two slices. There's going to be some probability of some things being more likely than others. Okay? So they designed the deep learning network to do that. And so this is the ground truth here. This is their method called deep resolve, and this is what you get if you did sort of the linear interpolation, which is sort of a standard approach. And you can see if you look at, so these are the sagittal images and coronal images here. What they found clinically is they can actually get the information that the clinicians want and have much better image quality. Okay, and so this is some work that is being used for musculoskeletal imaging and just showing that because of that nature of natural objects and images, that you can really get away with acquiring less data. Okay, and then sort of let the network figure out what should have been there, and in this case, you can go much faster then. Okay. So I think that's sort of a good place to stop. That's really where things are at. Basically, we're right in this middle of this transition between how much deep learning will be used to replace traditional image recon for all image modalities, not just MRI. CT is another great place for model-based reconstruction. Okay. So with that, we're going to stop a little early. So I'm going to go over some things, and then we'll have office hours later. So I did want to mention that there are a few classes being offered in winter 2020 that may be of interest to some of you. The follow-up course to this course is 280B, which is comparative biomedical imaging. It's going to be renamed Principles of Medical Imaging starting next year, I believe. And so it'll be a true 2-quarter sequence, which is going to be the basis of, the EE department has approved a new master's PhD program in medical imaging. So those of you interested could do that option. And bioengineering, I think, is going to approve a master's in medical imaging relatively soon as well. So those 280A and B will be the core classes, and they'll also have EE numbers if you want to take it as a EE course. Okay. So that's something that might be of interest to some of you. So that will cover things like ultrasound and PET and things that we didn't cover here, and also get into a little more of some of the advanced reconstruction. So that'll be taught by Francisco Contigoc, who is a professor in bioengineering and radiology. Okay. For those of you who really wanted to get some hands-on experience with MRI, one of my colleagues, Eric Wong, teaches BE280A, and so that's a lab course, so it's relatively limited enrollment, but you actually get to sort of do things on the MRI scanner and actually see what MRI is really about. Okay. And then I'm directing a class, a new class for next quarter which is being listed at Cognitive Science 260. That's fundamentals of functional imaging, and that's for if you really want to know what fMRI is about and how to analyze the data. So that's really meant for people who want to do fMRI. Okay. So with that, we're going to end early. So I'm going to end 10 minutes early so you have time to fill out the evaluations. So I think all of you received email about the course evaluations. So feel free to take this next 10 minutes to fill that out. And then I believe there's one for each professor and then for the TAs as well. So there's quite a lot to do. And then we'll start off maybe like 25 after the hour with the office hours. We'll go over quiz 2 from 2017. Okay? So are there any other questions before we break? Okay, great. So we'll recap in about 15 minutes.